Okay, this is the last chapter. It's kind of more of an appendix on color selection. I have been trying to explain color selection techniques now to many different NITARP teams. And if I knew what people trip on, I'd teach it better. I don't know what people trip on. And so it's possible that you just have to keep playing with the data until you get it. I don't remember what I tripped on when I was trying to understand color selection. So if I did, maybe I would teach it better, but I don't. 1 year, I tried getting really creative with my explanations of how this works. And I don't know if it was successful or not, but I'm going to share it anyway. I prepared in advance small Ziploc baggies, and one of them had peanut M&Ms that had 4 colors in them, which I said represented the known YSOs. Then I had a baggie of peanut M&Ms mixed in with all colors of plain M&Ms, which I said was going to be a mixture of young stars and dust-free stars. Then I had another baggie, which had peanut and plain M&Ms, but also some Skittles of the right colors to blend in, which I described ultimately, but not initially, as young stars, dust-free stars, and background galaxies, AGN. And then I baked some brownies with M&Ms sprinkled on top. And if you've ever done that, you know the M&Ms sink a little before they finish baking. And so you end up with brownie covering some of the M&Ms. And so those are the embedded YSOs. So I picked red, yellow, green, and blue to be class 1s, flats, 2s, and 3s for kind of obvious reasons, right? Because class 1s are the most embedded, and so they're red, and class 3s are the least embedded, so they're blue. Hopefully that makes sense. And then in this context, the follow-up spectroscopy is eating the candy to figure out if it's a peanut M&M, a plain M&M, or Skittles. So the way that it worked is, okay, we're going to first look at the sources in the known YSO bag. And I gave everyone like the little cellophane filters. And I asked them, do you understand how I'm getting the class 1 to flat analogs? And I asked them, you can't touch the bag, you can't turn it around. Can you distinguish the sources easily from each other with just one filter? Or is it easier when you have more than one filter to tell which one is a class 1 and which one is a class 2 and so on? Then I said, okay, let's look at the sources in the other bags and use the filters. How many class 1s, flats, and 2s are there in the other bags? Keep careful count, and I'll collect the answers in the end. And so I did. And the rules were that you can't pick the bag up because we can't ever go visit young stars or even see the cloud from a different angle. So pretend you can't visit the analogs. And you can't measure diameters because we can't resolve these YSOs. So pretend you can't resolve the M&Ms. So, and then I gave them the other bag, the final bag, and did the same thing, right? And asked them to do the same thing. And then I asked them to do spectroscopy and test which ones were peanut, which ones were Skittles, so on. So I then tried to have some reflections on this. Where does this model work and where does it fail? Well, the places where this model works is that we're studying first a population of known objects. So the first baggie just had peanut M&Ms. And then we're applying what you learned to a new region. And the new region had mixtures of peanut and plain, and then peanut, plain, and Skittles. And the objects do look different when you look at them through different filters, and the redder objects look even more different than the others given my definition of classes. And it is definitely easier to use more filters as opposed to fewer to find the sources that you want. When you try to apply what you learned to a brand new region, you can be fooled into thinking that things with the same color are the same intrinsic object because of the whole Skittles AGN analogy. And you really do need spectroscopy to decide if the objects are really young stars. The places where this doesn't work so well is that when you're doing this lab, you can measure the apparent sizes of the candies. And peanut M&Ms look different than plain in most cases. And in some cases, the really sharp-eyed kids will be able to read either the little printed M or the printed S on the candies. We can't generally measure the apparent sizes of young stars, and certainly we can't image their surfaces, at least at distances of more than a few hundred parsecs. So, and we're all in this lab, we're only using 3 optical filters, but in our project, we have measurements from many, many filters. In this context in the lab, we're only looking here for bright and dark and the RGB filters, but in our project, we have quantitative measurements of the brightness. Also, some sharp-eyed kid pointed out that the candies are reflecting light and the stars emit their own light. Yes, absolutely true. You can move around and measure the candies from more than one perspective, but we're measuring properties of objects so far away that we can't ever visit these objects in space or even get another perspective on them. It's also true that brownie isn't ISM. Our filters can't see through the brownie, but in real life, our filters can see through the dust in the interstellar medium. And spectroscopy is easy in the model because you eat the candy, but reality takes longer, and even then, the spectroscopy may not be 100% conclusive.